All right, quick analysis. The maximum number of items in a B tree of order M. So we're doing analysis here. We want to figure out what are the big O's of a B tree. Maximum number of items. Well, the root can have m minus 1 by definition. Level 1 can have m times m minus 1 because since the root is m minus 1, it can have m children. And each of those children are allowed to have up to m minus 1. Level 2 is m squared because each of those children can have, of course, m minus 1, etc., 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 down to level h where you have m to the h times m minus 1. So the total number of items are 1 plus m squared blah, 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 times m minus 1. Sum up all that because remember you can have it at the top down. And it roughly comes down to the maximum number of items is m times up raised to the height plus 1 minus 1. So when m is 5 and h is 2, that means a height of 2, you can have 124 elements. Okay. Well, if we use B tree of 101, then a tree of height 3 can hold approximately 100 million items. Why is this important? When searching tables held on disk, the cost of each disk transfer is the highest part, higher than anything else, but doesn't depend much on the amount of data transferred, as I point out, especially if consecutive items are transferred. So if we have height 3, then you only have to hit the disk 3 times in order to get to any item that is 100 million, where you have 100 million of them. Much better than the AVL. AVL, I think, what was it, 24? Yeah, 24. Oh boy. Huge improvement, vast improvement, although definitely more complicated. If we take m equals 3, we have what's called a 2-3 tree, because this effectively turns the B tree into a binary tree because it limits it to those 2 children. And you notice that we were going through a balancing routine with the B tree. So 2-3 tree is a balanced binary tree using the full B tree algorithm to do so. It's kind of overkill, but oh well. All right, comparing trees. Binary trees can become unbalanced and lose their good time complexity. AVL trees are strict binary trees that overcome the balance problem. Did any of y'all not do AVL trees? Just curious, yeah. In general, AVL is a good one to do. Heaps remain balanced, but only prioritized, not order the keys, because remember, it was holding a, the heap is a binary tree, but it's not a binary search tree. Multi-way trees, B trees can be M-way, and they can have any odd number of children. One B tree, the 2-3, is approximately a balanced binary tree. Perfect. The end. Any questions on B trees? Nope. All right. One, lab 2.1, lab 2.1.pdf. In this lab, we will sketch the steps of inserting, deleting from B tree. Draw each step of the insertion, delete. Yes, I know it's somewhat time-consuming, but use a LaTeX, then you're just doing a lot of copying and pasting. Just copy, paste, copy, paste, copy, paste. It'll make it easy. And here are your steps. You just insert all these numbers, and then I have you delete some, and then insert a couple more at the end. Obviously, this is designed so that it will force a couple things to happen. Just draw it out. There are multiple accepted solutions to this because, of course, there's different ways to bounce and rotate. Which direction did you choose? That is up to you. I only care about the PDF. So when you're over here and you're on Overleaf, you click this Download PDF button, and it downloads. Well, normally it downloads. Oh, here it is. I didn't see the pop-up. And then you can go ahead and save it. And just commit the PDF. And that's really all I care about. I'm going to save this code over here for you. There's already a template.txt or text file for you to start working on if you do it before I commit. Any questions? Okay. Well, that is all for today. I believe you have 2 labs and a project due tonight. Yeah. That's just how it happened. So, what's that? Is it 2? Or is it
Lab 19, I think.
just lab 19? Okay, good. Just lab 19. Oh, okay. 1 lab and a project due tonight. All right, that's all I have for today. I will see you on Wednesday.